In this video, I want to demonstrate that machine learning is possible on a quantum system. The main didactic goal is to give a first impression of how machine learning can be implemented on a quantum computer. And this video is meant to serve as an entry point for anyone interested in quantum machine learning and curious to see how such a system can work in principle. Important to say, quantum machine learning is a very complex and still emerging field. Whether there will ever be a practical quantum advantage in the area of machine learning is still an open question and subject of ongoing research. However, this is not the goal of this video. This video is meant to show, first, how a classical problem, the XOR problem, can be translated into the quantum world, and second, how a simple variational quantum classifier can be used to model and train such a problem on a quantum computer. The video is aimed at anyone interested in machine learning who wants to see what it might look like on a quantum computer, and anyone who wants to understand how a classical problem can be mapped into a quantum system. This video is divided into two parts. The first one, this video, focuses entirely on classical machine learning. In this part, I'll explain the basic principles of machine learning as clearly as possible and then simulate the process using code so you can get a better idea of how it works. The second part will focus on quantum machine learning, where we'll take the same machine learning problem and translate it into the quantum world. Let's start by looking at the problem we want to solve. We're working with the XOR algorithm. That means the output is 0 when both inputs are the same and 1 when the inputs are different. We use two input values, so there are 4 possible combinations: 0, 0, 0, 1, 1, 0 and 1, 1. And for 2 of them the output is 0, and for the other 2 the output is 1, as shown in the truth table. Our goal is to build a neural network, and if you're not yet sure what that looks like, don't worry, it will become clear during the explanation. What we want to do is train this neural network so that it learns to give the correct output for each of the 4 input combinations, without us explicitly telling it the rules of XOR. To be precise, we do give the network feedback each time, telling it whether its output was correct or not, but we don't hard code that. For example, 0 and 0 should give 0. Instead, we let the neural network learn the pattern itself. Of course, this is a very simple example and there's no practical advantage to solving XOR this way. We could just write an if statement. But it's a great way to demonstrate how a neural network works and how machine learning learns patterns from data. Alright, now let's move on to a general overview of the concept of machine learning, or more precisely, of neural networks. In this part, I'll present a general concept of how it roughly works, as simple as possible, without going too deep into the mathematical details, so that you can just follow along and understand the general principle behind it. It's possible that you might not be able to visualize some parts just yet. If you're interested in a deeper explanation, I'll show a code as example afterwards, where I go through every step mathematically in more detail. That should help you visualize things like what a neuron looks like more precisely. For those who are only interested in the concept, this section should be enough. And for those who want more, you can check out the code as well. So let's begin. At the start we have our inputs, which can be either 0 or 1. We have 2 neurons that represent our inputs, and each input neuron can only take the value 0 or 1 and nothing else. This doesn't apply to all neurons in the network, as we'll see in a moment, since the other neurons can take on different values. But the 2 input neurons can only be 0 or 1. Next we move on to the hidden layer. The hidden layer consists of neurons where the actual learning happens. It's the important part, so to speak. And I've labeled the hidden layer neurons as neuron 3 and 4. These neurons have something called weights. That means neuron 3 has a certain weight for neuron 1 and a certain weight for neuron 2. So what does that mean? Let's say the weight from neuron 1 to neuron 3 is negative, for example close to -1. Then if neuron 1 is 0, it doesn't matter, because it will be multiplied by 0 anyway. But if neuron 1 is 1, meaning it's activated, as we say, then this negative weight will inhibit neuron 3. So neuron 1 being active will cause neuron 3 to be less active. And if the weight is positive, on the other hand, then neuron 3 will be more active when neuron 1 is active. And the same thing applies for neuron 4. These two neurons, neuron 3 and neuron 4, then pass on their values to our output neuron, which I've called neuron 5. Again, there are weights, and this time between neuron 3 and neuron 5, and between neuron 4 and neuron 5. Now we want to present everything a bit more precisely using mathematics, so that it becomes clear how this is actually implemented. A neuron is, in the end, nothing more than a number, and this number is either directly given, like in the case of the inputs, or calculated, as we will see now. As mentioned before, neuron 1 and neuron 2 are the inputs, and these can only be 0 or 1. But neuron 3 and 4 are calculated based on those inputs. So now let's look at how neuron 3 is calculated. I call the value of neuron 3 simply N3, and this value is calculated as follows. N1, which is either 0 or 1, multiplied by the weight of neuron 3 for neuron 1. I write this as weight 3, 1, plus N2, again either 0 or 1, multiplied by the weight of neuron 3 for neuron 2. I write this as weight 3, 2, and then we add something at the end which is called B3. Now you might be wondering, what is this plus B3? And before I explain that, let's just look at neuron 4. Neuron 4 is calculated in exactly the same way, except that it uses the weights of neuron 4 for neuron 1 and for neuron 2, and the bias B4 instead of B3. So now, what exactly is this B3 and B4? These are what we call the bias terms. Why do we need this bias? Well, imagine both inputs N1 and N2 are 0. That would make both N3 and N4 equal to 0 because multiplying by 0 gives 0. And in that case, the network would be very inflexible because nothing would activate. But with this bias, we shift what's called the activation threshold. This makes the network more flexible and allows it to learn better. So, very simple put, the bias ensures that the neuron can still be activated even if the inputs are 0. If you want to understand this more intuitively, I recommend playing around with neural networks a bit. It becomes very clear why this bias is needed once you see how it affects the behavior of the network. Finally, let's look at the output neuron, which I call N5. In this case, the formula looks similar, but now we apply something called sigma, written as the Greek letter sigma, to the whole expression. So the formula becomes sigma of N3 times weight 5, 3 plus N4 times weight 5, 4 plus B5. This is basically the same as before, just with the sigma function applied to it. And what exactly this sigma means, I will explain in a moment. What does the sigmoid function do? The sigmoid function looks mathematically like this. Sigma of x is equal to 1 divided by 1 plus the exponential function of minus x. In our case, the x is always n3, n4, or also n5. I didn't say it before, but we also apply the sigmoid function at the end to n5, so to our output neuron. And why we do this has the following reason. Inside the hidden layer, we apply the sigmoid function to the neurons to create non-linearity. What does that mean? The XOR problem is a non-linear problem. That means when we draw the inputs like I have drawn them here in the diagram, then I have marked in red the inputs 0, 0 and 1, 1, and I have marked in blue the inputs 0, 1 and 1, 0. Of course, the inputs can only be 0 or 1, even if the x's in the diagram are written with decimal numbers. And what we want to do now is that we want to separate between 0, 0 and 1, 1, because they both should give the same output, and between 0, 1 and 1, 0, because they also both should give the same output. That means we need a line in the diagram that separates the values so that we can say these two values belong together and these two values belong together. And the way we have it so far, that doesn't work. Because until now everything is linear. So we can only create a straight line that separates the area. And the XOR problem is a non-linear problem. So we can't separate these four values with a single straight line. For example, like I show here, it's not possible. What we need is a curve, and the curve looks roughly like this, as I've drawn here. And with the sigmoid function, we can create such a curve. That's what we need the sigmoid function for in the hidden layer, to separate the values like this. In contrast, for the output neuron, so N5, here we apply the sigmoid function mainly because we want an output close to 0 or close to 1 in the end. That means we want to give the inputs like 0, 0 into the network, and we want the output neuron to become 0 or close to 0. And that's why we also supply the sigmoid function to the output neuron. And that's basically the function of the sigmoid function in short. So now let's take a look at the general process of how learning actually works. And one of the most important concepts here is something called backpropagation. I'll now give a quick conceptual overview of what that is so that everyone gets a clear idea of how the learning process roughly works. If you're interested in a more detailed mathematical explanation, you can check out the code part later on. So in the beginning, we initialize the weights randomly and the biases as well. As we saw earlier, we have two neurons in the hidden layer, each of which has two weights, and the output neuron also has two weights. On top of that, each of those three neurons has one bias. Now once we've initialized everything, we feed in our first input. For example, the input 0, 0. Then, as we discussed earlier, the value of neuron 3 and neuron 4 is calculated, the sigmoid function is applied to both of them, and finally the value for the output neuron is calculated, again followed by applying the sigmoid function. This gives us a value between 0 and 1 at the output neuron. And this value will of course be pretty much random because the weights and biases were completely random to begin with, which means the computation is random too. So we get some number as an output. What we do now is the following. We take that output value, let's say for example it's 0.6, and subtract the actual target value we were aiming for. In our case, we passed in the input 0, 0, so the expected output would have been 0. That means we calculate 0.6 minus 0, which gives us a value of 0.6. This is what we call the error. If our prediction had already been exactly 0, the error would be 0, meaning no adjustment would be needed. But in this case, the error is 0.6, and that's the value we want to reduce. Now if you think about it for a second, the output we got was the result of all previous computations, and those computations depended on the weights and biases. So this error is actually a function of all the weights and biases involved. What we now do, and again I won't go into mathematical detail here, is that we adjust all the weights and biases in such a way that this error becomes smaller. This is done through something called the gradient descent method, which I'll explain in more detail later when we look at the code. Next we pass in a new input, for example 0, 1, run it through the network, calculate the output, calculate the error, and again adjust the weights and biases to reduce the error. We repeat this process many times, thousands of times in fact, for all of 4 possible input combinations. And what ends up happening, and this is not immediately intuitive, is that the weights and biases adapt in such a way that the output is always close to 0 for input 0, 0 and 1, 1, and always close to 1 for input 0, 1 and 1, 0. Now we're going to build a Python program that creates the neural network we just discussed. A network that will learn the XOR algorithm. We'll start by importing 2 libraries, namely math and random. The math library will be used for some basic mathematical functions we'll need later, and random allows us to generate random numbers. In the next step, we define our sigmoid function. We create a function called sigmoid, which we'll later use in the network. It simply returns 1 divided by 1 plus the exponential of minus x, which is the exact definition of the sigmoid function as I mentioned before. After that, we define another function called sigmoid derivative. This is simply the derivative of the sigmoid function. We'll need this later on when we implement backpropagation. For now, the important thing is just to understand that this function returns the derivative of the sigmoid function. You can verify on your own that this really is the correct derivative. Now in the next step, we define our weights and biases. First, we define W1, which contains the weights for the neurons in the hidden layer. We define them in form of a matrix, and it actually doesn't matter whether you know what a matrix is or not. What's important to understand is that we store our weights inside this variable W1. And the way we do this is we have an array, the W1 array, and inside this array we have 2 more arrays, each representing 1 neuron in the hidden layer. Later, we can access a specific weight by writing something like W1, 0, 0. This calls the first array inside W1, so this array, and then the first entry inside that array, so that one here. And this gives us exactly the value of that weight. For each weight, we use random uniform -1, 1, and this means we randomly choose a number between -1 and 1. And that's all this function does. So in this matrix, each entry corresponds to 1 weight. Then, in the next step, we define a vector called B1, which holds the biases for the 2 neurons in the hidden layer. We define them together in a simple array. And finally, we define W2, which represents the weights for our output neuron, and B2, which is the bias for the output neuron. Now in the next step, we define our forward function. We pass in x, which is our input, and based on this input and the corresponding weights, we then calculate the value for the 2 neurons in the hidden layer, and from those, the value for the output neuron. I've already started here with C1, which represents our first hidden neuron. I used a different name earlier in the explanation, but it really doesn't matter. Here we just call it C1. So C1 is equal to x0. Later on, we'll define the input as an array with 2 values. So x0 is just the first entry, meaning the first input neuron. Then we multiply that by W1, 0, 0. Like I explained earlier, this means we access the first array in W1 and take the first entry inside that. Then we add x1, which is the second value in the input array, so the second input neuron, and multiplied by W1, 1, 0, which is the weight connecting the second input neuron to the first neuron in the hidden layer. And finally, we add B1, 0, which is the first value in the bias vector for the hidden neurons. And then below that we have A1 equals sigmoid C1. And what we're doing here is we pass the value C1 into the sigmoid function and store the result in A1. And in the next step, we do exactly the same thing again, this time for the second hidden neuron. And this we call C2. Just like before, we then calculate A2, which is simply the sigmoid function applied to C2. And once again, we repeat the exact same process now for the output neuron. But this time, of course, we don't use the original input neurons as inputs. Instead, we now use the already computed values A1 and A2. So we multiply those by the corresponding weights for the output neuron, add the bias for the output neuron, and apply the sigmoid function to the result. That gives us A3, which we then store. Finally, we return all these values using return. So whenever we call the forward function, all of these values will be returned. We'll use them later on in the backward function, which we'll define shortly. So now we move on to the backward function, which represents our backpropagation. This function is a bit longer, and for better understanding, I'll first go through it briefly and then later come back to my notes where I'll explain in detail how this works for a specific weight. Because explaining it directly in the code would be a bit too complicated. So we define the backward function, and right at the beginning I've added the line global W1, B1, W2 and B2. These are our weights and biases where all parameters of the network are stored. Why do we need to define them as global? Because if we don't explicitly declare these variables as global, then any changes we make to them inside the function will only be local changes. They won't affect the weights used in the rest of the code. So the model wouldn't actually learn anything, and that's why we must declare them as global. Then in the next step, we call the forward function once and unpack the values it returns, just as we defined them earlier. That means we assign the outputs C1, A1, C2, A2, C3 and A3 to variables with the same names here inside the backward function. Technically, I could use different variable names, but I've chosen to use the same ones here for clarity. So far, it's still quite simple, but now comes the slightly more complex part. As you can see, there are quite a few lines of code now, where we calculate all the derivatives, the partial derivatives we need for the gradient descent step. What these derivatives mean and why we have to compute them, I'll explain in a moment. Now there's one last important part to point out, this lower block of code right here. This is where we actually update the weights. We loop through the weights using two for loops. So here, 1 over I from 0 to 1, this line, and 1 over j from 0 to 1, this one. What we're doing here is, and remember when we're saying range 2, it includes 0 and 1, but not 2. That's just how Python works. What we're doing here is looping over every individual weight in W1, and then we update that weight. The update is written using this notation. And this simply means take the old weight, subtract the learning rate multiplied by the derivative of the loss with respect to that weight and assign the result back to the same weight. And how we compute these derivatives is defined in the lines above, so here, where we calculate all the necessary gradients using the chain rules. And the same thing we did here for the weights for the neurons in the hidden layer, we do here for the bias of the neurons in the hidden layer, and here for the weights of the output neuron, and here for the bias of the output neuron. I'll now explain in my notes step by step how to compute this gradient for a single example, like the weight W100, which is the connection from input neuron 0 to the hidden neuron 0. Now I want to give a clear example for one individual weight so that the steps of backpropagation can really be understood. We already saw earlier in the code, and I'll show it again, that the new weight is calculated as the old weight minus the learning rate times the partial derivative of the loss function with respect to that weight. Why does the formula look like that? It's actually quite simple. We start with the old weight, which we'll call W old, and then we subtract a factor, the learning rate, multiplied by the derivative of the loss with respect to that weight. The learning rate is just a parameter that controls how big each step is. In other words, how much we change the weight. This is important because if the steps are too large, it might prevent us from ever reaching the optimal weight. And then we have this derivative dl by dw, and what it tells us is the slope, how much the error changes when we slightly vary that weight. If the derivative is large and positive, that means the error increases quickly if we increase the weight, and we want to do the opposite. We want to decrease the weight, and that's why we subtract this value. Because if the slope is positive, the error increases, and we want to lower the error by lowering the weight. On the other hand, if the error gets smaller when the weight increases, then this derivative is negative, meaning there's a downward slope, and that tells us that we should increase the weight. So if the derivative is negative, we end up subtracting a negative number, which means we're actually adding something, and the weight gets larger. And that's where this update formula comes from. Underneath, I also wrote out the loss function again. It's the true value, which I called y true in the code, minus a free, the value that the output neuron returns, and that all squared. We square it simply so that we only get positive errors and no negative ones. Here is an example for one specific weight. Let's take the weight of neuron 3 with respect to input neuron 1, which is called W100 in our code. I'm using the code notation here, but of course the principle is always the same. So what do we have to do? To compute dl by dw100, we need to apply the chain rule multiple times. We first need to compute the derivative of the loss L with respect to A3, the final output of the network. Then we need to compute the derivative of A3 with respect to C3, since A3 is the sigmoid activation of C3. Then we compute dC3 by dA1 because C3 is calculated as A1 times W20 plus A2 times W21 plus B2. So the value W100, which is the weight of the first hidden neuron for the first input, lies inside A1, which lies inside C3. So next we need the derivative of A1 with respect to C1, because again A1 is the sigmoid of C1. And finally we need dC1 by dW1 0, 0. Why? Because C1 is calculated as x0 times W100 plus x1 times W110 plus B10. And W100 is exactly the weight we are currently investigating. Once we have all these derivatives, we just multiply them all together using the chain rule. So what do these individual derivatives look like? dl by dA3 is simply minus 2 times y true minus A3. That's just the derivative of the squared error loss. Then dA3 by dC3 equals or is the derivative of the sigmoid function which we already defined earlier in the code. And here you can now clearly see why we defined that as a separate function. dC3 by dA1 is simply W20 because C3 equals A1 times W20 plus A2 times W21 plus B2. Then dA1 by dC1 is again just the sigmoid derivative evaluated at C1. And dC1 by dW100 is simply x0, the first input of our input vector. And that's how we get the full chain of derivatives for this one specific weight. Of course, this principle is not only applied to this one weight, but also to all other weights and biases in the network. So yes, it's a lot of derivatives to compute, but the core idea is always the same. And that's exactly what happens inside the backward function in our code. Alright, now that it's hopefully clear what's going on and why, let's quickly summarize everything. We have our backward function, which takes two inputs. First, the input vector x, that's two values, either 0 or 1, representing our input neurons. And second, y true, which is the expected or correct output. Then we declare our weights and biases as global, so the function can actually update the values globally and not just within its own local scope. Next, we call the forward function once to get all the values we need for the derivatives here. Based on these values, we calculate all the partial derivatives in this block. And finally, using those derivatives and the learning rate, we update the weights and biases. And that we are doing here. That completes one training step, and with that, we are one step closer to having optimal weights. The idea is that after enough steps, when we pass an input like 0, 0, the output will be as close as possible to 0, which is what we want. After that, we define our learning rate. I've already explained what this does. Here I just set it to 0.1, and that's a solid and practical value to start with. Then we define the number of steps. This tells us how many training steps to run. In other words, how many times we go through the whole process of adjusting the weights. So through this whole process here. I just picked 10,000 here. I tested a few values, and with this learning rate, you need at least a few thousand steps to get good results. Maybe 5,000 would also be enough, but 10,000 works for sure, and anything more isn't really necessary. And finally, we define our actual data here, because up to this point, the network doesn't even know what it's supposed to learn. We define all four possible input combinations, 0, 0, 0, 1, 1, 0 and 1, 1, along with the corresponding outputs that we expect. 0 for 0, 0 and 1, 1, and 1 for 0, 1 and 1, 0. Alright, and now we're already at the final part of our code, the part where we actually put everything together and call our functions. We start by defining a for loop. For step in range steps. And what does that do? It simply loops from 0 to 9999 because we defined steps 10,000, and in Python range steps goes from 0 up to, but not including 10,000. So we'll run the entire training loop exactly 10,000 times. In each iteration, the variable steps increases by 1. So it's step 0 in the first one, then step 1 in the second, and so on. And each time we run the full training step that follows. Then inside that loop, we define a second for loop, for x, y in data. Now what's happening here? Python knows that data is a list of pairs. More precisely, a list of tuples where each element looks like this. Here defined in data. So when we write x, y in data, Python automatically unpacks each tuple. So the first tuple, for example, 0, 0 and 0. And the first value, the input 0, 0, goes into x. And the second value, the label 0, goes into y. So for every single training example, we then call backward x, y, and x is the input, so this array, and y is the label 0. This means we pass the input and the expected output to our backpropagation function, backward, which does a full forward pass, computes all the gradients, and updates the weights accordingly. And once all 4 training examples have been processed in one round, we go back to the outer loop, increase step by 1, and run the inner loop again. And that entire process repeats 10,000 times. So actually, we're not running the whole thing just 10,000 times, we're running it 40,000 times. Because inside each of the 10,000 steps, we go through all 4 data points in our dataset. In the very last step, we add a small piece of code to track our progress during training. We write if step modulo 1000 equals 0, then, and the percent sign means modulo, that is the remainder after division. So this condition is true only when the current step is divisible by 1000 without a remainder. If you think about it, the only values for a step that satisfy this are 1000, 2000, 3000 and so on. So this block runs exactly 10 times. Inside, we first define a variable called total loss to keep track of the total error. Then we run another loop for x, y in data. And here we go through each training example, calculate the output of the network using forward x, take the last returned value, which is the output of the final neuron, compare it with the expected value y, compute the squared difference, the error, and add it to the total loss. Finally, we print the step and the loss. And how this looks like, I show in a moment. Now, when we run the code, we see the individual steps being printed. Step 0 also fulfills the condition because the remainder, so the modulo, is also 0 in that case. So step 0 gets printed along with the loss value to the right. We can see that the loss starts at around 1.04, which is obviously quite high. After 1000 steps, the loss drops to 0.98, but that's still not great. So we can already see that 1000 steps wouldn't be enough. After 2000 steps, we see that the loss is down to 0.74, which is still not great. And after 3000 steps, we are at 0.12, which is much better. After 4000 steps, we are at 0.029, which is quite good, and so on. And then with step 9000, we're at a loss of 0.0049. And as we will see in a moment when we test the network, that's more than enough to get almost always the correct output. Now in the final step, we test our trained neural network. We go through each possible input 0, 0, 0, 1, 1, 0 and 1, 1 and run the network 1000 times for each one. I won't explain the code here because it's pretty straightforward and not really necessary to go through. As you can see, the model gives the correct output every single time. 1000 out of 1000. So it's perfectly accurate for all inputs. Now for those of you who have a bit more mathematical background, there's one more interesting point I'd like to mention. What we've used here is the gradient descent method, and it can happen that our gradient vector gets stuck in a local minimum. Whether this happens or not often depends on how we randomly initialize the weights. In theory, you could just try many random starting weights and pick the ones that work, but that kind of defeats the purpose. If you imagine the loss landscape in 3 dimensions, the gradient descent might lead us into a local dip, a minimum, from which we can't escape. And even though there is a deeper global minimum somewhere else, the algorithm just gets stuck. That's exactly what I've visualized here. I trained the network a few more times until I found such a case. You can see that for one input, specifically 0, 1. The network never gives the correct result. It always returns 0 when it should be 1. That's a classic case of being stuck in a local minimum. So we get 0 out of 1000 correct predictions for that input. It's a good reminder that this neural network is not perfect, because it's extremely simple by design. But that's okay, it was just meant to illustrate the basics. At this point, we've reached the end of this 2-part video. I hope you now understand the basic ideas behind machine learning and you're ready to take the next step, applying these concepts in the quantum world. Thanks for watching and I hope to see you in part 2.